Welcome, everyone. Today we're going to be looking at related rates, and we'll see why it's called that in a second, but this is, well, really kind of related to the idea of implicit differentiation. And so we're going to be looking at an equation involving two variables. So maybe something like this: x squared plus 5y squared equal to 36. So when we look at this equation, what do we see? We see an x and we see some y's. What we're going to do is we're going to introduce a third variable, and we're going to call that variable t. And this is really going to stand for time. So what we're going to do is we're going to treat these other variables, x and y, as really implicitly defined functions of t. So we're going to treat x. This is an implicit function of t. And we're going to treat y as an implicit function of t. Or think of it as time. So we're going to think of x as changing over time, and we're going to think of y as changing over time. So really what this means is we're going to be treating x as both a function and a variable in our equations. And same thing for y. We're going to be treating y as both a function and a variable. And t, that's just going to be a regular variable. And so when we have an equation like this, and what we're going to be interested in is figuring out, well, how does x change over time? So we're going to be interested in calculating the derivative of x with respect to time. And same thing for, y. If y is changing over time, well, then it's going to be good to know how fast is y changing over time. So we'll also calculate things like dy dt. And so because we're treating each of these variables, x and y, in our equation as both a function and a variable, we're going to take our implicit differentiation technique and give us a mechanism for how to differentiate these terms. So whenever we see an x term in our equation, when we differentiate with respect to time, we're treating x as both a function and a variable. So that means we're going to do two things. We're going to differentiate it just like we normally would. So that's the variable part. And then because we're treating x also as a function, we're then going to multiply the result by x prime. Or if you want, you could just use the dx dt. And then same thing for y. We're going to be treating y as a variable, so that means differentiate the thing like usual. And then we're also treating y as a function, so that means we're going to have to multiply the result by y prime. Or if we want, we could call it dy dt. And so the way to kind of picture what's going on here is our equation. This is sort of the geometry. And so you almost want to picture this, the situation here of a related rates problem. One way to kind of think of it is like a particle that's moving along the graph of the curve. So think of it as, here's our curve all graphed out. It's an ellipse. And we have our particle here at some point. And what's happening is this particle is moving along this ellipse. And so what dx dt tells us is the velocity in the x direction, and the derivative dy dt tells us the velocity in the y direction. So this particle is going to be kind of moving along the curve. And what this equation does is it tells us kind of the path of the particle. Only tells us the path of the particle. But then we introduce this third component, this time component, which gives us the motion around this ellipse. And so that's what we're going to see. We're going to see how to differentiate, how to calculate these derivatives using kind of our implicit differentiation technique. So let's actually work with that. So example 5, we're going to suppose x and y are both differentiable functions of time t. And we also know that x and y are related by this equation, x squared plus y squared plus 5y squared equals to 36. So again, that's giving us the ellipse. And what we're going to do is we're going to calculate the derivative dy dt at a time when x is equal to 4, y is equal to 2, and dx dt, the x derivative, is equal to 5. So we know kind of 3 pieces of information here, and we want to figure out what our y derivative is. And so the way we're going to do this is kind of similar to our implicit differentiation technique. So we're going to start with our equation, x squared plus 5y squared is equal to 36. And then we're going to go through and we're going to apply the derivative to each distinct term. So we're going to apply the derivative to the x squared. We'll apply the derivative to that 5y squared, and then to the 36. All right. So now we differentiate. So for this x squared, we're going to start by differentiating it like usual, so 2x. And because we differentiated just an x term here, we're also going to multiply that result by x prime. Because again, what are we doing? We're treating x as both a function of time and a variable. So that means the variable part means we differentiate it like usual. The function part means we then multiply the result by x prime because of chain rule. Then we get to our next term, which is the 5y squared. So we differentiate that just like normal. So we bring down the 2, multiply it with the 5. So we get 10y. And then because we're also treating y as a function of time, we multiply that result by y prime. And then on the right side, well, derivative of 36, again, just a constant, nice and easy, just going to be 0. And for the sake of having our notation match up, let's just rewrite our x primes and y primes with the dx dt and dy dt. So we'll just write this as dx times, or 2x times dx dt, plus 10y times dy dt, and this will all be equal to 0. And so this equation here, we call this our related rates equation. And we can see why it's where the name of this topic comes up is essentially what we're doing is we have this equation and there are 2 derivatives in it. There's this x derivative with respect to time and there's this y derivative with respect to time. So derivatives measure the rate of change. And so this equation gives us a relationship between these 2 rates of change. So related rates equation. So essentially a related rates equation for us is going to be an equation containing both derivatives, the x derivative with respect to time and the y derivative with respect to time. All right, so at this point, all we need to do is plug in all the different pieces that we know. So in this case, we know that our particle is at point, or has an x coordinate of 4, so that's one of its current locations. We also know the y coordinate of the particle is at y equals 2, so we know where y is. So what we're going to do is just plug in all the information. So we know x is equal to 4, y is equal to 2, and then we also know our x derivative is equal to 5. So we're just going to plug in. We're going to evaluate. So what do we get when we do that? Well, we're going to have 2. And then instead of x, we're going to plug in where we know this particle is. So at x coordinate 4. And then we know how fast it's moving in the x direction. So we know it's moving at a rate of 5. So we'll plug in 5 there for the dx dt. And then, well, we have 10y. So let's fill in what we know y is. So 2. And then the thing we don't know is this dy dt. So we're just going to leave that as is. So dy dt there. And then all this will be equal to 0. Then we just clean up all the arithmetic, do all the arithmetic here. What do we end up with? Well, 20 times 2 is 40. And then we have 10 times 2 is 20. So we have 20 times dy dt. And then we just solve this equation for dy dt. So we solve for whatever missing derivative that we're interested in. So in this case, our y derivative. And what we get, or how we would do this, is I would subtract 40 from both sides, and then that would get rid of it over here, and then we would divide both sides by 20. So when we do that, we end up with our y derivative is equal to negative 40 over 20, which is negative 2. And so we can kind of have an idea of how this particle is changing. The y-coordinate is changing at a rate of negative 2, so the y-coordinates are decreasing, and our x-coordinates are increasing at a rate of 5. And so if we go back up, this is where our particle is to this little picture here. And we know the x-coordinate is increasing, and we know the y-coordinate is decreasing. So that's telling us that our particle is moving kind of in this direction. So there's really two options for where this particle could be moving. But there's only one direction that gives us x values that are increasing and y values that are decreasing. And it's along this section of the curve. So we kind of know how fast it's moving in both the x and the y directions. And so that's this idea of related rates. What we have is we have a geometric equation that gives us kind of the path our particle is moving. And then these x and y coordinates, well, we're going to treat those just like variables like they really are. But then we also treat them separately as these implicit functions of time. So a particle that's actually moving around the ellipse. So there's a third variable here. And when we differentiate our equation with respect to time, and that's what we're doing here, we're differentiating with respect to time. So the prime notation is good for shorthand, but it doesn't tell us what we're doing the derivative with respect to. So what we're doing here is the derivative with respect to time. So we're seeing how the x and y coordinates, essentially the rate of change over time. All right, so we're going to try one more example like this in class. So we'll see you there. Bye-bye.